Okay, so following up on the last section, we're going to go through the script page now, and I'm going to explain to you the various components that that's available for you, that are available for you for building scripts. Now you'll see in the first section we have timers. Well, this configure section is broken up into three parts, starting with timers. Then we have the actual digital pins, and it ends up with a remote section here. Now, timers, these components are useful if you require timers, obviously, in your application. If you want some condition, if you want some statement to execute only after a certain time has elapsed, you will use timer functions. If you want, say, on the press of a button, a door should open and it should stay open for 10 seconds only, you will need a timer for that. If you want to record temperature or humidity readings every 30 seconds, you will require a timer for that. So this is typically what timers are used for. Now the digital sections here, these are only the digital pins, the 6 pins at the back and the 1 pin in the front, in which you can connect either sensors as input or all kinds of other devices like motors and switches to it, for output purposes. Well, maybe not a switch as an output, but still you get the idea. As for the remote, if your microcontroller is to communicate with another microcontroller or with a web server or something out there, then you will specify, well, at least HTTP support for your microcontroller to be able to communicate with something else. So starting from the top, we are going to add a timer. Now you'll notice we've got 2 timers in here. The reason why we have 2 is just to allow for the flexibility if you require 2 different timers to execute at the same time. Say, getting back to our door example, you want the door to stay open for 10 seconds, but at the same time you also want to record temperature readings every 30 seconds. Then you will need, you will run your script with 2 timers in it. Do bear in mind that you can reuse timers. So if you need a timer for a specific purpose and you're done with it, you can stop the timer and you can redeclare it, you can use it for something else. So considering that, it's not to say you only have 2 timers, but you have 2 timers that can run concurrently. So we have enabled a timer now. You can enable the second timer if you need it, but for simplicity, we're only going to stick with the first timer now. Now I'm going to skip over to the remote section, just briefly explain this. Under remote, you'll see that you've got 2 available, I don't want to say sensors, but you've got 2 available options here. The first one is HTTP GET. This is, HTTP or Hypertext Transfer Protocol is in essence the protocol that the internet is built on. So leveraging from that, this option will allow you to communicate with a web service somewhere on the globe, or you will also be able to make web calls to one of your other microcontrollers so they can communicate via HTTP. Another option in here, definitely preferable for home automation and the like, is Mqtt, which is a lot faster, but the caveat is that we don't have Mqtt server running on the microcontroller itself. The server or the service is a bit too big to run on the microcontroller, so we do need something with an operating system like a Raspberry Pi or one of our Orange Pi components to run a Mosquitto broker. If we have a Mosquitto broker on our local network, selecting this option here will allow us to communicate with it. So we're just going to specify HTTP. Now, getting to our digital sensors here. Here you will see a list of all the sensors available. Bear in mind, as I explained before, after each and every month we will release new firmware. The new firmware will have additional support. We'll have support for more sensors. So this list will become longer and longer and longer until we can support everything that there is. Now I'm going to skip the first one and I'll explain that one last. You'll see for the rest of the sensors, they start with the word in or out. This indicates whether it's an input sensor or an output device. So buttons, PIR sensors, these are all input into our microcontroller. So it can read, for example, whether a button is pressed or not. Whereas when we go over to out, a DC motor, it's going to write to it. So it's going to tell the motor how fast to run or stop. Or, typical commands like that can be written to an output device. The external input, you'll see it starts with I/O, which means it's an input and an output device, but I'll explain that one once we're done with these. So the first sensor here is just a button. Now we've got two types of buttons. You've got a push button, you can just press, and the microcontroller will be able to tell you whether this button is pushed or not. But we also have switches, so state switches. So if you switch it to on, the microcontroller can tell you this switch is in the on state or it's in the off state, and then depending on that input you can do something with it. You can sound an alarm, or you can open a window, or whatever it is that you're going to build in the end. PIR sensor, this is a passive infrared sensor. It's very much, well, not very much, it's exactly the same actually as these sensors you use in your alarm system at home. That red eye that's looking at you from the corner of the room? That's a passive infrared sensor. Now, in our case, exactly the same. It's going to state that there's no movement detected until you start, your footloose sequence in front of it. Then it's going to tell you there's some motion in the room. And then once again, you can respond to that. Read switch. Also using alarm systems at home, a read switch is just a magnetic switch. So like these door contacts you have in your alarm system, there's a little switch with another magnet that you bring close to it. And the moment you remove the magnet, the switch is going to complain. It's going to say someone took my magnet, and you will be able to detect that on your microcontroller and do something meaningful with that information. Next one here is probably the most popular sensor. It's temperature and humidity sensor. You can use this to, just to check what the temperature is like in a remote room, or what the humidity is in a server room, for example. If the humidity is 100%, it means they're in a sauna, so your server's probably not going to survive. Anyway, once again, just your eyes and ears into the microcontroller solution, these in sensors. Tilt sensor, very simple example of a tilt sensor is just a mechanical switch that can detect whether the sensor is actually on its side, or whether it's straight, standing on a table somewhere. I don't know why you would want to use a tilt sensor on the microcontroller itself, but perhaps you have some idea as to a door. When you open up the door, or a lid or something, if you remove it, the tilt sensor will be able to tell you that it's open or it's upside down, or the idea is here just to give you the building blocks that you can use to build your own solutions with. Ultrasonic sensor, next one, neat little sensor that detects distance. So it just emits an ultrasonic frequency, and that frequency is being bounced off of walls and other objects, your forehead, and it will read that back and calculate the time between when it was sent out and when it was received, and it will be able to tell you how far the object is away from the sensor. So if you have a grandma that can't park at all, it's very good to put one of these in front of the garage, and you can put like a little LED board on there with an indicator saying that, you can come grandma, you can come still, or, you should have stopped already. It's just something that you can use once again to build your own solutions with. In terms of output, we've got a DC motor, nothing fancy about a DC motor. I mean, we've been playing with DC motors since we were kids ourselves. It's, the motors that you get in all your racing cars, well, not large racing cars, I mean these radio remote control cars. If you specify DC motor here, you can, write to it, and you can set the speed at which it should run. Now, of course, it's easy to tell it run at full speed or stop, but these microcontrollers have what we call PWM, or pulse wave modulation. Now, pulse wave modulation allows us to run at a duty cycle. So we can tell the motor to run at 50%, which means it's just going to pulse it. Instead of sending a steady stream of electricity, it's going to pulse the motor, and the motor is actually going to run at half its speed. So it appears that it's just using half the voltage, but it's just a trickery. Some clever guys managed to put together to run a motor at half speed. Now, the same technology like PWM that we use for motors, we will also be able to use for the buzzers and the LEDs. Piezo Buzzer is actually a vibration sensor, but you can use it to emit sounds as well. So it's not a siren, but you will be able to compose your own little melodies and make nice little sounds, door chimes and stuff with piezo buzzers. LEDs, once again, just a little light emitting diode. You can switch it on full time, switch it off, or you can PWM the crap out of it, which means it's actually going to look like it's dim. But it's not. It's just you're only pulsing it with electricity every now and then. So it's actually flickering very fast, but it looks like it's being dimmed. Next, very popular option here is a relay. The relay, in essence, is just a mechanical switch that allows for an external circuit to be completed. So the nice thing about the relay is that it allows you to interface your microcontroller solution with any other system that you already have. Say if you want to start the pool pump, or you want to electrocute your mother-in-law, you can use a relay for that. So if, say, you use the timer and you say activate the relay after 30 seconds, then once the 30 seconds is passed, it will just open up the relay and boom, goodbye mother-in-law. Now the last one here is just a servo motor. Servo motor is unlike a DC motor. Servo motor is a very unique motor in the sense that it's not spinning like a normal motor. It rotates into a desired position. So we've configured these, we've configured the IDE to run from 0 to 180 degrees. So you can specify that the motor should be at 78 degrees, for example. Servo motors, a very popular choice, especially amongst hobbyists. If you build model airplanes, or once again, radio remote control cars, the steering, all of that is being done through servo motors. If you've seen the video of my robotic arm on the web as well, that robotic arm is built up from 6 servo motors, one controlling each one of the fingers, and there's another servo motor in the wrist. And so it takes only one servo motor to flip someone off. So that's a list of all the input and output sensors that we have available in version 0.7 of the firmware. So perhaps the time when you go through this video, you'll see you've got some more options in there. Now, for simplicity's sake, oh yes, we've got the external input in here as well. I almost forgot, saved the best for last. Now, your microcontroller is an isolated system. It's running its own firmware, it's running its own script that you're building now, and you can't interfere with it from outside, especially if it's password protected. You need to log into it and change the script before you will be able to, do anything different with it. But external input allows you to expose a particular pin to an external entity. So if you want your microcontrollers to communicate with each other, you're going to dedicate a pin for that purpose. So let's say pin 1, in this case D01, we're going to specify as external input. Now, if we've done that, we're not going to physically connect any hardware to that pin, but it might as well have been that we had a button connected to that pin. So if you press the button, that pin can read, the button is pressed or not. But if it's an external input, it means that it's going to receive input from an external entity, but it's still going to be either high or it's going to be low, or you're going to write some analog value to it in between that you can relay through to the rest of your application. Now, external input, you're only going to use external input, obviously, if you require one microcontroller to set the state of another. So let's specify D1 as external input, and D2 we can specify as a button. D3, let's put some output devices on here. Let's say we've got a DC motor on there, and we have a servo motor on here, for example. Now looking at the script section, the setup part will run only once. It will run first, but then it's done running. Whilst the repeat section goes without saying, it will continuously execute until you power down the microcontroller. Also, if you set your script to run automatically and you give power to your microcontroller again, the setup section once again will run once, and the repeat section will continue to execute until you come back to the screen and you stop the execution here. Now, some items like the timer, you will declare in the setup section. So if you click on add, you see under condition we have always and only if. Now always means that whatever follows your condition will execute. Regardless of what the current state of affairs is, it will execute always. If you specify only if, you first need to specify a condition which needs to evaluate to true before the following condition will be executed. Since we're busy with a timer, we're going to say always. And now if you look at the list of pins, you'll see all of them are listed as out. You may notice that not all of them are output devices, like D2, for example, is a button. So if we have D2, how can there be an out? Just investigate a little bit and take a look at the rest of the options, and you will find that you only have a store function here. Now store means that it's going to take the current value or the current state and it's going to write it to a file, a data file on the microcontroller. So you can use the store functionality to take periodic readings of temperature in a room, and you can store that in a file for view or for use later. So you can see that, at 3 o'clock in the afternoon, the temperature went too high. Now in this case, for a button, if we store this into a file name, which we can call anything, buttons, it means that every time, well, not under the setup section, keeping in mind under the setup section, this is only going to run once, but it's going to run, it's going to look at what the state of the button is, it's going to check is it pressed or not, and it's going to write the result into the file system under a file called buttons, which you can then view afterwards by going to the file system. So as you see, we don't have any systems in the data subfolder. So once we do, we can view them from there. What we do want though is the timer. So we have declared the timer and it comes up as timer 1 out. And you'll see we have start value, stop, and once again store. Now store will only mean that, if we specify the timer should run every 10 seconds, it's going to write into the file every second that it hasn't run yet, it hasn't run yet, it hasn't run yet, and after 10 seconds it's going to tell you, okay, the timer has executed. So maybe it sounds a bit meaningless to store the results of a timer, but consistency is key. So for all the input and output devices, we can store the value or the state of such in a variable. So we're going to say start value. You always need to specify a start for each one of your timers. Although you have a timer, the script or the microcontroller has got no idea for how long the timer is, when it should execute. So we start off by saying start value, and then this is the assignment operator. You can see it's looking for seconds, and now we can specify in the variable field, we can specify 10 seconds. So this is going to take our timer and it's going to execute it, or it's going to set the state every 10 seconds. Now, what's important here is to remember when you declare timers like this, specify them in the setup section, because if you specify them in the repeat section, this repeat section runs very fast, and it continues to run. So what's going to happen if you specify it in here is you are going to set your timer to 10 seconds. And then before that 10 seconds elapsed, you're going to run this statement again. You're going to say you have a timer execute after 10 seconds. Before it can execute, you're going to set it again. So what's going to happen is you're going to keep on resetting your timer, and it's never going to, to trigger or to execute, because you keep on resetting it. So in order to prevent that, set them up in the setup section here, or if you do it in the repeat section, you're going to need to specify an if then else statement and just specify, where your timer needs to be declared in order to make sure that you do not repeatedly recreate it. So the only thing that we want to run in the setup section in this case will be the timer. So then we move over to the repeat section. And once again, we have always and only if. If we specify only if, now you will see that where we had all the out options in there, we will have the in options in here. It's because we need to read input for a comparison now. In order to do a successful comparison, we need some input. We're on the comparison condition, so D2 was our input button. So it's going to compare that its pressed state, and now you have operator, which is not the assignment operator anymore, it's the comparison operator. So it's equals or not equals to, and then it's comparing it against a state, and the variable will be on or off. So this literally means if D2, which is a button, if the button attached to D2 is pressed and it's in state on, so if it's pressed, in other words, then do something. Of course, the then do something follows. If we add a new line, we'll see we have then. Forget about the and or for now. Just focus on the then. So if we specify then, now we have all the out options again. So now we can look at our motor, for example. Do we have a motor, a servo motor, which was attached to D4. So now we can say D4, and because it's a servo motor, do note that for all the different sensors and devices that you can connect to it, it's very context sensitive, so each one of them have their own set of menus or options. If the button is pressed, then servo should turn to the leftmost position. Very small, simple program. Then we can add. You'll see we still have a then option there. Despite the fact that we've specified a then, we still have a then, because we can continue specifying then items. The script is going to see them as a block. So if the top condition here is true, it's going to keep on executing the then statements until it reaches something else, until it reaches an else statement or an always statement or another only if statement. So if we change the then to an else, we can say we want D4 again, and it should turn right. So what we have in this case is we're going to check continuously, is the button pressed? If the button is pressed, then turn the servo motor to the leftmost position. If the button is not pressed, turn it to the rightmost position. But we also have a timer in here. We want to do something with our timer as well. So once again, we have multiple else statements if you wanted to continue on executing else statements, but we want to start something new. So let's say only if. And now we are looking at our timer. So if the timer is triggered, very much the same as when the button was pressed, is the button triggered? Yes or no? If it is triggered, then let's see what we've specified up here. we still have a DC motor. Then our DC motor should run at full speed. Otherwise, our DC motor should stop. So what this means, once we start running this code, is that if the button attached to D2 is pressed, then turn the servo to the left, otherwise turn the servo to the right, and then regardless of whether the button is pressed or not, check if the timer time has passed. So if 10 seconds passed, then run this motor at full speed, otherwise stop it. But since this code runs continuously, this section of code here, the last 3 lines, will result in, after every 10 seconds, the motor will run for 1 second. Because it's going to reset the timer again, and then the motor is going to stop. If we want to build more advanced examples, say we want to combine these, for example, we can just delete these lines. And now we can say if the button is pressed and, see there's and or there, just forget about the 001 for the moment. If we select the and option and we say the time is triggered, this results in the check as follows: is the current button pressed and has the time been triggered, or the timer been triggered? So has 10 seconds passed and the button is pressed. If we select or, it's going to check whether only one of the two is true. So either the button is pressed, but if you don't press the button, then execute whatever follows anyway every 10 seconds. If you want to include multiple nested ifs, you'll see that the numbering starts changing to 001 and 002. Still have ands on ors, but now we can specify a 002. Now, these numbering, it just refers to precedence or rank in the sort, which means that it should first compare all the level 001 variables before it starts comparing it to level 002. Just like in mathematics, if you have an equation and you have 2 plus 2 times 2, you need to execute the 2 times 2 first before you sum the last 2. It's just order of precedence or rank. Now this works exactly the same way. If you need to compare 2 objects first before introducing a third one, then you're going to do the comparison on the first 2 objects on the level 001 before you start comparing them to 002. If you have 4 objects that you would like to compare, A and B should be compared on one level, and C and D should be compared on a second level, and then the result of each should be compared on a third level. You will specify saying that the first 2 should run on level 001, the next 2 should run on level 002, and then automatically the sum of all of these will be compared to give you a meaningful result in the end. So this might be a little bit confusing at first to those of you who aren't very familiar with programming terms and concepts, but you don't need to worry about it too much in the beginning. You will soon enough get the gist of it and start using it if required. So of course, once we've built our script, we can try to execute it. But before we can execute it, we need to give it a name first. So let's call it my first. It's definitely not my first, but let's lie. It will give you feedback saying that the script was successfully saved. If you go back to your file system, let me just refresh, you will see now that there is a my first script running in a subdirectory called scr. Now you can delete your script, or you can just view it. It's a bit arbitrary, so it's just for curiosity's sake that you will be able to view this. But since you can view it, you can also download these scripts and you can save it somewhere else. Do note though that all your scripts and all your settings and everything, even if you do upgrade the firmware, your files will still be present. We're not going to overwrite the files on your system. Also, this file system, like mentioned before, if you store the value into a file, then that file will also be available here, but it's going to be available under a data subfolder. Let's just change this back to 10. Now we've saved this script. You'll see the compile button is grayed out. It's because we've made some changes to our script now, so we should save it again. The moment we've saved it, we will be able to compile the script. Now, if I click on compile, it should show you that compilation was completed successfully, and then we can run our script. In this case, our script's actually not going to do anything. It's just going to do a comparison, and it's going to see, yes, it's true or it's not, but it's not going to write any output because we haven't specified, a then statement, for example. Just to show you the compile functionality, say we write a then statement. So what do we actually have here? If the button attached to D2 is pressed, or the button is pressed and the button is pressed. What a lot of rot. But anyway, obviously it's going to be true and it's going to execute then. So let's save it quickly. Compile. See that all the lines are green, which means it's good. But now we're going to insert a line in here, and let's try and break this. I'll try to make this as hard as possible to break. I can probably, yes, let's put another only if in there. Let's delete these lines and put only if, then a then, and then we delete the if. So now, if we try to compile our program, it's going to tell us that there's a problem, and you won't be able to run your script because it starts off with a then condition, but there was no comparison done beforehand. So this is not a legal script. You won't be able to run this at all. So just go back and then either delete the line or just fix the condition so that you will have a healthy script in the end again. Okay, and the next tutorial I will run split screen, and I will demonstrate to you exactly what it looks like when we run servos or motors or LEDs from a script. So, thank you so much for watching.